Hi, I'm Susan Callery. I'm based at NASA's Jet Propulsion Laboratory in Pasadena, JPL for short. No, we don't make speakers. JBL is an audio company. We get that from time to time. Anyway, JPL is one of 10 NASA centers around the country, and 3 of them are actually in California. I'm currently the managing editor of NASA's climate website. Previously, I led JPL's Earth Science public engagement team, which was responsible for all Earth Science communications outside of traditional media. I also created and co-led a NASA-wide team that coordinated Earth Science communications across the agency. You already know I'm here because I represent NASA, but I'm also here because of these two. Even though I'm 68 years old, I'm here because I want them to have bright futures. And I'm here because I see the data every day. I'm here because I believe in NASA and the amazing people who dare mighty things every day. I'm here because I've seen our engineers solve incredibly complex problems millions of miles away and feel if it's not impossible, it's not worth doing. I'm here because I see the impact of our work and what it has on the world. I'm mostly here because I can't give up. I'll probably be buried gripping a keyboard. I'm also here because my partner, who I've known for almost 50 years, worked for an oil company. I'm making up for his transgressions. So I'm going to give you a lot of information today. There's just so much material to share. It's really hard to know where to draw the line. What I promise is that if you have questions, my team and I are available to answer your questions through our website at climate.nasa.gov/feedback. This is how science was communicated in the past. Presentations were so complex and jargony that you just feel left out. Luckily, we've advanced well beyond confusing science, and we now include science communicators and multimedia to help convey complicated information. It's really an ongoing challenge. We're always trying to do better. But I want to give you an example. I was in a meeting with a group of scientists and project managers and a few science communicators. We were discussing satellite altimetry, which measures the height of things, the ocean or ice or trees, something like that. Now, I know what altimetry is, but I basically interrupted and said nobody in the public would understand the term, and the scientists and engineers started arguing with me. One of our communicators who taught oceanography in community college, so she was both a communicator and a scientist, said, "Susan's right. Let me give you an example." So a friend of mine is a meteorologist who went out on a blind date. They exchanged pleasantries, and then he politely asked his date what she did for work. I have no recollection of what she said. And she turned around and asked him the same question. He said, "I'm a meteorologist." She said, "Oh, so you study meat?" So how are JPL and NASA involved in Earth and climate science? Most people have no idea that NASA has been studying Earth since the very beginning. NASA was founded in 1958 and launched its first weather satellite in 1960, and we've been studying Earth ever since. Fast forward to today. Not only do we study climate, but we study all of the aspects of Earth, from the land to the water to the atmosphere, and how they all work together to create the conditions for life. We study how water and carbon move through the planet. We study sea level. We study agriculture. we study natural and man-made disasters and weather and air quality. Climate crosses all of those areas. We have a large fleet of satellites, 27 to be exact, and instruments in space to help us keep eyes on the Earth. But before we jump directly into the science, I want to acknowledge a few things. One, the climate has always changed over geologic time due to natural causes. Two, fossil fuels have helped us create a vibrant economy and have improved our quality of life. Three, climate change is a really difficult topic to discuss. Four, what is happening now has already negatively impacted our economy and will continue to do so, and will affect jobs, our health and security, and our exposure to political instability. 5, even though NASA is precluded from advocating for any policies, our role is to provide the best possible scientific evidence to decision makers. 6, humans are amazing. I wish you could spend a day in my shoes. But the future is up to us. We have the tools and we have the technology to slash our emissions and ensure a livable planet for future generations. Okay, here we go. Earth's climate system is complex, but climate change is actually pretty simple. I'll show you why. Climate scientists like long time scales and think of different parts of the planet as systems that all function together to create the various processes on Earth. With this perspective, I'll give you climate change in less than 50 words. We've removed carbon from stable geologic storage and burned it, releasing carbon dioxide and methane and other greenhouse gases. In doing so, we've changed the chemical composition of Earth's atmosphere. More CO2 in the atmosphere gives us a warmer atmosphere. Less CO2 gives us a cooler atmosphere. This relationship has been true throughout almost all geologic time. If we want to prevent the planet from getting even warmer, we need to stop burning fossil fuels. It's really that simple. Climate science isn't new. We've actually known about the greenhouse effect, our blanket of gases in the atmosphere that hold in warmth from the sun, since 1824, and that our pollution from burning fossil fuels would warm the planet since 1896. And since those early days, as we have more and more measurements and better technology for measurement, the science has only become stronger. I hate to start with the basics because I'm sure you probably all know this, but I want to discuss quickly the difference between weather and climate because we get that question a lot. And the difference is basically a measure of time. Weather is what conditions of the atmosphere are over very short periods of time, what you see in your weather forecast on your app on your phone or on TV. Climate is the average of weather over time and space, usually over a period of at least 30 years. You can kind of think of it as climate is your personality and weather is your mood. So how do we know that our climate is changing? Well, we have a lot of measurements from satellites, from instruments on aircraft, from instruments on the International Space Station, from ships, from buoys, from instruments on the ground, and more. Here are Earth's surface temperature changes that have been measured on the ground since 1880. You might want to pay attention to the year you were born. And just as an aside, these measurements are based on a baseline of 1951 to 1980. So that's why you see the -1 degree C and the +1 degree C. This is not based on the 1850 to 1900 baseline. This beautiful, beautiful graphic is from our scientific visualization studio at NASA's Goddard Space Flight Center in Greenbelt, Maryland. They just do beautiful work. So another way we know that climate is changing is by looking to the past. There is an entire field known as paleoclimatology that uses indirect forms of evidence, such as ice cores and tree rings, that can be used to infer climate. And if you look at ice core data from the last 800,000 years, we can see these rhythms and pulses of CO2. We can also see we're well outside of that natural pattern. Here's a nice visualization of the changes in temperature since 2002. Now, these are measured from space, not from the ground. Humans have increased the concentration of CO2 in the atmosphere by 50% since 1750. And you can see here, the darker the color, the higher the CO2 concentrations. We're actually now at 419 parts per million. And for reference, if you look at temperature for the last 24,000 years, you can see we came out of the Ice Age about 10,000 years ago and then experienced this long, extremely stable period of temperature And this is when modern human society and modern agriculture really developed, and where life flourished and started to thrive, and where the population really started to increase. If you look at the red line at the end of the graph, it shows we've left that period of climate stability. The future is up to us. We have the tools and technology to ensure a livable planet for our children, grandchildren, and future generations. We have it. So let's talk a little bit about the causes of current climate change. It's you and me. It's the greenhouse gases, primarily CO2 and methane, produced by human activities, primarily from burning fossil fuels. The human footprint has become immense and has had a dramatic impact on our planet and its climate. We have become our own geologic force. Here's the breakdown by source. You can see that transportation and electricity take up just a little bit over half of our greenhouse gas emissions. Then industrial practices take up another 24%. And that's rounded out by residential and commercial and agriculture. All of these activities produce greenhouse gases. Greenhouse gases are gases that trap heat. I'm sure you've seen greenhouses. They're full of windows that let in sunlight, and that sunlight creates warmth. But a greenhouse doesn't let that warmth escape, and that's really how greenhouse gases act. They let sunlight pass through the atmosphere, but they prevent the heat from the sunlight from leaving the atmosphere. And natural greenhouse gases are a good thing. Without them, our planet would be too cold, and life as we know it would not exist. But there can be too much of a good thing. Scientists know that human activities are adding too many of these gases to the atmosphere. The difference between greenhouses in the real world is that they control for temperature, water, nutrient supply, as well as insects. That's just not the case in nature. So here's a great animation of the greenhouse effect. Sunlight reaches the earth. Some of that energy is reflected back into space, and some is absorbed and re-radiated as heat. And that heat is reflected in all directions, warming the earth. So this is a scary number. In 2022, humans emitted 40.6 billion metric tons of CO2. 1 metric ton is 2,200 pounds. This is 1 metric ton compared to a double-decker bus. That's a lot of CO2. And we hear people say a lot, well, CO2's been higher in the past. Well, the issue today is that CO2 in the atmosphere hasn't been this high in at least 3.6 million years, long before humans walked the earth. Some studies show even longer. We are uniquely adapted to the conditions that we really started to grow and thrive in. So, how do we know that this increase is due to humans? And we know because CO2 from burning fossil fuels has a distinct fingerprint or internal structure that instruments can measure. So you may say, so why should we care? And the reason is because Earth is essentially a closed system. Our atmosphere is very thin. Not only that, but some CO2 lasts for a very long time in the atmosphere. Longer than the history of civilization and even longer than nuclear waste. The future is in our hands. We have the tools. We have the resources to start reducing our CO2 emissions. So now that we've talked about the causes, let's talk about the effects. I've already shown you the increase in surface temperature, but I really want to start talking about the ocean. This is one of the most important points I want you to take away today. Believe it or not, the ocean takes up most of the heat from our greenhouse gas emissions, over 93%. The atmosphere takes up a very small percentage. It really takes a lot of energy to heat water. In spite of that, the ocean is overheating. And by the way, I really hate graphs. Sometimes it's all we have. And just for your information, a joule is a unit of energy. As a result, the top 700 meters or 2,300 feet of the global ocean has warmed about 1.5 degrees Fahrenheit since 1901. So all you really need to take away from this graph is that it's getting warmer. So a study by 23 researchers from 14 different institutions determined that ocean temperatures in 2021 increased by about 14 zettajoules. That's a lot of joules, which translates to the planet's oceans absorbing the heat equivalent of 7 Hiroshima atomic bombs detonating every second for a year. And as a result, sea level rise is accelerating. Over the course of the 20th century, sea level started to rise early on about 1.5 millimeters a year. There are about 25 millimeters in an inch, so really it wasn't much of a big deal. But since the 1990s, sea level has been rising at about 3.3 millimeters per year, and currently we're tracking at about 4.8 millimeters per year. While a few millimeters of sea level rise may seem small, scientists estimate that every inch of sea level rise translates into 8.5 feet of beachfront lost. Just since 1992, sea level has risen about 4 inches. Here's a visual of sea level rise from NASA satellites between 1993 and 2019. Darker areas represent higher sea level. And you can see it's not uniform, it's different around the world. Some areas are impacted more than others. And this is due to wind patterns and ocean currents, and also the topography of the seafloor. So for context, here's the last 3,000 years. This shows that sea level has risen more during the 20th century than any previous century in the past 3,000 years. U.S. scientists concluded that by 2050, average sea level along the U.S. coastlines could rise by about a foot above today's levels. But there are significant regional differences. Here's our projection for Port San Luis by the end of the century, and this projection is about 1.7 feet. 40% of the population in the U.S. may be vulnerable to sea level rise by the end of the century. Not only that, but think of everything that exists along the coast: homes, hotels, railroad tracks, roads, bridges, power plants, sewage treatment plants. That's a lot of infrastructure to have to move by the end of the century. Continuing with ocean impacts, we just can't forget coral reefs. This is an image of a bleached coral in the foreground and a healthy coral in the background. And this is a picture from the Great Barrier Reef. The IPCC special report, that's the Intergovernmental Panel on Climate Change, which is a body that's convened by the UN, but the reports are written by thousands of scientists from all over the world who are experts in their field, and they volunteer their time to comb through all the research from the previous IPCC report, in this case, the last 7 years. And it says that ocean warming, ocean acidification, which is like adding lemon juice to the water, and more intense storms may cause coral reefs to decline by 70 to 90% at 1.5 degrees Celsius warming, becoming all but non-existent at 2 degrees warming. This is a big deal because this is the basis of the ocean food pyramid. We're pulling the foundation out from under the house. The future is in our hands. We have the tools and the technology to do this, to bring down our carbon emissions and try to offset the worst impacts that our children and grandchildren are facing. So let's look at the effects of global warming on the frozen regions of our planet. Scientists call this the cryosphere. So we've had satellites in space since 2002 that act like giant scales in the sky, and they weigh or measure changes in both frozen and fresh water. And by the way, these satellites were jointly developed by NASA and by the German Space Agency. So between 2002 and 2011, Greenland, which is in the Arctic, lost an average of 277 gigatons, or 277 billion tons of ice each year. Antarctica lost an average of 151 gigatons, or 151 billion tons of ice a year. Also note that Greenland is melting faster because the Arctic is warming 4 times faster than the rest of the planet. For reference, 1 gigaton, which is a 1 with 9 zeros after it, is the equivalent of 400,000 Olympic-sized swimming pools. I'll let you do the math because I can't possibly do it. Okay, looking at sea ice. So we tend to measure the maximum and minimum annual sea ice extent, particularly in the Arctic. This is a look at the minimal annual sea ice extent over a short period of time in the Arctic. And we know that it has decreased by 12.6% per decade since 1979. There's a lot of complex science behind this that I can explain later if you would like. You can email me through our feedback section, and I'll be happy to explain it to you. Suffice it to say that there are 3 measures of sea ice: its age, its volume, and its extent or area, all of which are declining. So working from a combination of satellite records and submarine sonar data, NASA scientists constructed a 60-year record of Arctic sea ice thickness. Right now, Arctic sea ice is the youngest and thinnest it's been since we started keeping records. More than 70% of Arctic sea ice is now seasonal, which means it grows in the winter and melts in the summer, but does not last from year to year. I'm not showing Antarctic sea ice here, but it was increasing slightly for a number of years, and then the last couple of years it has reached record lows as well. Moving on to glaciers. Scientists have been monitoring the world's major glaciers since 1970, and these are scientists from all over the world. These glaciers lost the equivalent of slicing more than 90 feet off the top of each glacier. And this matters because glacier melt provides drinking water for millions of people. And melting glaciers and ice sheets are the biggest cause of sea level rise. So here's an example from Tibet. Here's 1987. Here's 2021. Here's the Columbia Glacier in Alaska, 1986, 2019. These images are part of our Images of Change gallery on our website. If you go into Explore, the Explore tab on our website, you can go to Images of Change, and there are hundreds of images of all kinds, land and ice and fires and human footprint. So next, I want to shift to extreme events. US billion-dollar disasters are rising. And here we are back to the IPCC report that says, human-induced climate change is already affecting many weather and climate extremes in every region across the globe. Evidence of observed changes in extremes such as heat waves, heavy precipitation or rainfall, droughts, and tropical cyclones, and in particular, their attribution to human influence has strengthened since the AR5. The AR5 was the last report that came out, I think 7 years ago. So going back to our satellites jointly developed by NASA and the German Space Agency, scientists have confirmed that major droughts and periods of excessive precipitation or rainfall have been occurring more often. They also found that the worldwide intensity of these extreme wet and extreme dry events, and intensity means a combination of extent, duration, and severity, is closely linked to global warming. The economic impacts are being felt around the world, though the human toll is most devastating in poor and developing nations. I'm sure you're all curious about all of these atmospheric rivers that have been battering California in the last few months. Research suggests that climate change will increase the risk of extreme rainfall events along the Pacific coast. And although scientists have not directly connected these atmospheric rivers and the extreme rainfall that we've been having, we know that as Earth's temperature warms, the amount of water vapor in the atmosphere increases. And in fact, for every degree Celsius, water vapor increases by about 7% in the atmosphere. In 2018, NASA led a study showing that climate change is likely to intensify atmospheric rivers across most of the globe by the end of the century, although their number may decline a little bit. A study in August of 2022 from the University of Colorado Boulder and UCLA showed that climate change is increasing the risk of a California mega flood. The study projects that atmospheric rivers will be significantly longer and wider than the ones we observe today, leading to more frequent and intense atmospheric river conditions in affected areas. You can sort of think of them as rivers in the sky. So here are a few examples of extreme events that have been tied to global warming. Here's one from earlier in 2023. It's called Cyclone Gabriel in New Zealand, and it was 4 times more likely because of climate change. And then if you look back to January 2023, there were massive heat waves in Argentina and Paraguay and huge wildfires. That was 60 more times likely because of our warming. The 2019 European heat wave that killed a lot of people was 100 times more likely because of our greenhouse gas emissions that are warming the planet. Hurricane Harvey in 2017 was 3 times more likely because of global warming. And what we're finding is that hurricanes are slowing down a bit, so they're dropping more rainfall. It's interesting. This image just blows me away. This is Tropical Cyclone Freddie, which occurred last month, the longest lived tropical cyclone ever recorded. And it's hard to tell the geography from here, but that big island is Madagascar off the coast of Africa. And by the way, I've been there. It's an amazing place. If you like lemurs and animals, it's a really cool place to visit. So it just persisted and persisted and persisted and persisted and persisted. Okay, let's move on to land impacts. Satellite data is really important for food farming. We use data collected from space and from aircraft to map agriculture worldwide, and we work with partner agencies, organizations, farmers, fishermen, and decision makers to help understand everything from global supply outlooks to water use to what crops to plant and when. And climate change will affect agriculture around the world. The effects are becoming more and more apparent as we see more record-breaking heat waves, intense droughts, and shifts in rainfall patterns. Even though more CO2 is good for some plants, that is only part of the recipe for success. Plants also need stable temperature, stable water and nutrient availability, and stable insect behavior. All of these change as we add more CO2 to the recipe. Think of what a cake would be like without flour. One of the things we've seen in North America, but around the world in pine forests, is we're seeing a lot of pine trees dying from bark beetle infestations. And those are beetles that lay their eggs in the winter, and the larvae develop over the winter, but a lot of them die off because they don't survive very well in cold temperatures. But as winters become warmer, and winters are becoming warmer faster than summers, more and more of these larvae survive. And so we have more and more bark beetles that are attacking and killing trees. A study that just came out from NASA, just 2 weeks ago maybe, looked at crop yields globally for corn and wheat and found that corn yields will probably decrease by about 24% by the end of the century if current climate trends continue. Wheat, on the other hand, may see an uptick in crop yields. But what happens with wheat is its nutritional quality declines. Five of California's 10 largest wildfires on record happened in 2020, and the state set a new record for acres burned. Between the early 70s and 2018, California's annual wildfire extent increased fivefold, with a 90 to 100% probability due to drying fuels from global heating. Fires are more intense. Fire season is now 2 to 3 months longer than it was 20 years ago. Okay, so now that I've given you all the bad news, there is good news. Let me first say that NASA does not advocate or lobby for any policy or solution. Our job is to inform decision makers so they can make choices based in science. However, we are working on some new technologies that should help. And this first one's kind of cool. So NASA funds small businesses for groundbreaking research. Here's an example of working with a company called Microlink Devices to reduce the cost associated with solar cells that work in space. And this technology could serve as an alternative source of space propulsion, such as solar electric propulsion driven by high-power solar arrays. It can provide unprecedented efficiencies for vehicles, solar roof tiles, power plants, and more. These are already being used by troops in the desert as a source of portable renewable energy. NASA's Glenn Research Center in Ohio is also working on high-efficiency, low-cost, easy-to-manufacture solar cells. These will also have a low environmental impact. And we're starting to see more and more companies working to recycle solar panels. So Caltech is the sister agency with the Jet Propulsion Laboratory. Caltech actually manages JPL for NASA. So a group at Caltech is working on solar fuel technologies that use sunlight, water, CO2, and nitrogen from the air that can readily be used in our existing energy infrastructure. And solar fuels are sustainable and able to produce no net emissions of CO2. Another lab at Caltech, the C Group, are working on lithium-ion batteries. And these batteries are already being reused and repurposed and then recycled, but even newer batteries are coming. The next generation battery research is moving beyond lithium-ion. And the C Group is working on using more abundant, sustainable, and less expensive materials. Here's another cool piece of news that came out very recently. The U.S. Postal Service is buying 9,250 electric vans starting later this year. Okay, here's another kind of cool thing. So dealing with methane is kind of a low-hanging fruit. We've been collecting methane data from aircraft for a number of years. However, we launched a new instrument on the International Space Station in the summer of 2022 called EMIT. And it looks at dust sources around the world and their impacts on climate. But the instrument can also measure and pinpoint methane emissions. And so far, scientists on the team have identified more than 50 super emitters in Central Asia, in the Middle East, and in the southwestern United States. Super emitters are typically leaking pipelines, landfills, large cattle ranches that emit methane at very high rates. And being able to identify the sources allows NASA scientists to contact the facility operators so that they can make changes or repairs. And that's already happening. And actually, on their website, you can click on these plumes of methane and you can remove that layer and see exactly the name of the facility that is releasing the methane. So once again, I'm just so thrilled to be here. I am honored to be asked to be here. My team and I are available to answer your questions. And you can reach us anytime at climate.nasa.gov/feedback. We have a wonderful team of communicators and scientists who help answer these questions. Thanks very much for having me.